All right, another molecular scenes problem, this time looking at depicting what's happening in a precipitation reaction. So we had our first molecular scene problem at the beginning of this chapter when we talked kind of about solutions, and now we're going to see one as it applies to precipitation reactions. So 4 parts to this reaction. The first two parts actually ask us to identify who is in each of these beakers. 4 possibilities for each beaker. So we're going to go through and kind of look at these options and see what we might be able to rule in or rule out. So let me write down here below the options that we have for beaker A. We've got potassium chloride, sodium sulfate, magnesium bromide, and silver sulfate. Well, if we look at what we see in terms of the ions, we can see that we have a monovalent cation and a divalent anion. And this isn't like the first problem where they maybe had things that were not in the right ratio. This has things in the right ratio. There are 10 cations here for 5 divalent anions. So that's right. But we need to see which of our species down here matches that. Well, hopefully everybody sees I can rule out potassium chloride because this has a monovalent cation and a monovalent anion. So this has both monovalent cation and anion. So we're going to rule it out for that. Sodium 2 sulfate. Well, we have a monovalent cation and a divalent anion. So maybe this guy's it. But let's just double check and make sure that there's not something we're overlooking. And let's look at our other options here. Magnesium bromide. Well, this is going to be the opposite situation. This has magnesium as a divalent cation, and we'd have twice as many bromide monovalent anions if we were to have this solution. That's not what we have here. So that's the opposite. Okay, so we're not going to have that guy. Well, sodium sulfate still looking pretty good, but let's look at silver sulfate. Oh boy, silver is a +1 cation and sulfate is again a -2 anion. So that looks like it could fit too. The only thing that we're forgetting is if we look at table 4.1 and we consider sulfates. All common sulfates are soluble except those of calcium, strontium, barium, silver, and lead. So silver sulfate is not soluble. Silver sulfate is insoluble. So it would not dissociate in solution. So for that reason, we can rule out silver sulfate. And so beaker A is sodium sulfate. Let's go through the same analysis that we have for the options given to us for B. So again, B shows us a divalent cation and monovalent anion. So we've got ammonium nitrate, magnesium sulfate, barium nitrate, or calcium fluoride. Well, even as I'm writing these down, again, rule out this one because this is monovalent for both cation and anion. Can rule this guy out because it's divalent for both cation and anion. Barium nitrate, oh, that's a possibility. Divalent cation, monovalent anion. Oh boy, but so is calcium fluoride. Well, maybe we need to do the same treatment that we did over here. Nitrate, barium nitrate. All common nitrates so are soluble. Let's just double check. We've got this calcium fluoride. All common fluorides are soluble except those of lead and group 2A. Grabbing my periodic table again. Calcium's part of group 2A. So that calcium fluoride is insoluble. So again, we can rule this guy out because calcium fluoride is insoluble. So we've determined now what is in each of these solutions. So the compound that's dissolved in beaker A, sodium sulfate. Compound B is barium nitrate. Part C asks us here, name the precipitate and the spectator ions when solutions A and B are mixed. Write balanced molecular, total ionic, and net ionic equations. I'm going to try to start taking my shortcut here. I'm not going to ask you guys to write total ionic equations. I think they take a long time to do, And it's important to be able to kind of see what's going on without necessarily having to write out all the species all the time. There are going to be times when we'll do that, but not every time. So let's see if we can do this here. Let's first write our balanced molecular, because that's usually the easiest one to write because we're writing everything together and then we swap partners and so forth. All right, sodium sulfate, we know that that's an aqueous solution. We're combining that with barium nitrate, again another aqueous solution. When we do these precipitation reactions, we want to swap partners. And so again, we have a cation going with a new anion. So let's try sodium nitrate. I can already see that that's going to have a 2 in front of it in order to balance. And you know what? I've looked at table 4.1 enough that I know all sodium salts are soluble, all nitrate salts are soluble. So I'm going to leave that with an AQ. All right, and now we're going to have barium sulfate. Barium sulfate. Go back to table 4.1 here. All common sulfates are soluble except barium. So barium sulfate is not soluble. Okay, so there's our precipitate. All right, now I'm going to see if we can take our shortcut here to write our net ionic equation. And what I'm going to be doing is mentally looking at stuff at the right and the left side of the equation and seeing if it's present the same. Sodium ions. Sodium ions. So sodium is a spectator ion. So I'm going to write all my spectators over here. Sulfate ion. Sulfate solid. I'm not writing sulfate as a spectator, so sulfate must be part of my net ionic. Barium ion. Barium is part of my solid. So I need to include barium ions as part of my net ionic. Nitrate ions. Nitrate ions. So nitrate, again, can come over here as a spectator. Anything that's going to be solid is always going to be part of your net ionic equation. And there's our net ionic equation. If we wanted to write the total ionic equation, I'd write sodium aqueous on each side, nitrate aqueous on each side. But I really want to get you guys to try to see who the spectator ions are without having to write that net or that total ionic equation. All right, I'm going to have to get a new piece of paper here because our last part of the problem, I need a little bit more space. This tells us if each particle represents 0.1 mole of ions, what is the maximum mass of precipitate that can form, assuming we have a complete reaction? Well, wow, this tells us that we have 0.1 moles of ions here, 0.1 mole of ions here. I shouldn't say 0.1 moles, looking at the number of particles. So we've got information given about each of the reactants. That should scream bells and whistles that this is a limiting reactant problem. All right, so I'm just going to flip over here so I have a little bit of room here. We're going to write this equation again. So our net ionic equation is the only one that's really important. And again, I'm going to look at my molecular scenes and I'm going to count how many of these ions we have, because it tells us that each particle represents 0.01 moles of ions. So if I'm looking at my barium sulfate, which is our B solution, so I'm going to just make a little note. This is our B beaker, and I need to count our sulfate ions. Oh wait, no, I'm sorry. Sodium sulfate came from A. My apologies. Sulfate came from A. I knew I was wrong there because I was looking and I didn't see any divalent anions. 1, 2, 3, 4, 5 of these. So we have 5 sulfates, okay? We know that they are worth, as it tells us, 0.010 moles each. So this means that we have 0.05 moles of sulfate. I'm going to do the same treatment here. This is our B beaker. In our B beaker, we got to count divalent cations. 1, 2, 3, 4. So we've got 4 Ba2+. Again, add 0.010 moles each means that we've got 0.04 moles of Ba2+. All right, now this becomes a limiting reactant problem just like we've done all along here in Chapter 3 and are now bringing into Chapter 4. We're going to take each of these reagents and we're going to walk from moles of this to moles of product, and we're going to see who makes the least. And you might be able to see this already because the stoichiometry is 1 to 1 to 1, that this is not going to be our limiting reagent because we will make the same number of moles of product, which is less than this. But I want to treat this the same way that we've treated our other problems so that if you need a review on limiting reactants, you can see how to do it. We've got 5 sulfate ions. Again, I'm just kind of walking through this step here. Every ion that we see is worth 0.01 moles. And so we've got 0.05 moles of sulfate. From our balanced chemical equation, we know that 1 mole of sulfate will make 1 mole of barium sulfate. And that's equal to 0.05 moles of barium sulfate. Do the same thing with our barium ions. We counted 4 barium ions. They're worth 0.01 moles apiece. We've got 0.04 moles of barium ion. Again, 1 mole of barium ion is going to give us 1 mole of barium sulfate. And that's 0.04 moles of barium sulfate. We make less of this, so this guy is our limiting reactant. When you're doing limiting reactant calculations, the rest of the problem is dependent on this calculation. So 0.04 moles of barium sulfate. The problem asks us what's the maximum amount of precipitate we can make, so we need to walk then from moles to grams, and we use molar mass for that. 233.4 grams is the molar mass of barium sulfate. We could make 9.3 grams of barium sulfate. Okay, so if I went through this limiting reactant problem a little bit quickly and it's a little bit confusing, maybe go back and review the limiting reactant problems from Chapter 3.